Good morning, everybody. Today we will continue with mechanical waves. If you understood the simple harmonic motion, periodic motion, which we have discussed during the last lecture, this mechanical waves will be very easy for you to understand. What we have within this chapter, we will learn how to use relationship among speed, frequency, wavelength of a periodic wave, and we will also learn how to calculate the speed of waves on a rope or string. In addition to that, we will learn what happens when mechanical waves overlap and interfere. This is very important for musical instruments. This will produce standing waves. And we will learn the properties of standing waves on a string and have to analyze these standing waves. And then finally, we will learn how string instruments produce sounds of specific frequencies. Then with this last part of the lecture, we will finish this topic. So, let me discuss the importance of mechanical waves for our daily life. Here you see a picture from a city which is destroyed due to the earthquake, because earthquake waves carry enormous power as they travel through the earth. So mechanical waves carry the power, carry the energy, okay? And they travel in the medium. And there are also other mechanical waves, such as sound waves or vibration of strings of a piano. And they also carry the energy, but they carry far less energy compared to the earthquake waves. And the mechanical waves can interfere, and when they interfere, they produce standing waves, and this information helps us understand musical instruments. So we will discuss all these things within this chapter. Let me start with the types of mechanical waves. We will learn transverse wave, we will learn longitudinal wave, okay, and we will discuss the difference between transverse and longitudinal waves. Here we have a string. Okay, you see this is a string and this is hand. And by using hand, by applying force one end of this string, you can produce a mechanical wave on the string. So the hand moves the string up and then returns, producing a transverse wave that moves to the right. So what do you see here? You produce a disturbance here, and then this disturbance travels to the right. What is the meaning of transverse wave? Why we name this wave as a transverse wave? Because the displacements of the medium are perpendicular or transverse to the direction of travel of the wave along the medium. So let me explain like this. Here, just consider we have a particle. On top figure, I put a particle with red color, okay? So what do you see? What is the position of this particle? This particle moves up and down, okay? This is the motion of the wave, motion direction of the wave, okay? Wave travels to the right, but the particles on the string does not move to the right. They stay at the same position, but they move up and down, okay? Here, if you have particle, it moves up and down. So here we have the statement, the displacements of the medium, the displacements of the particles on the string are perpendicular or transverse to the direction of the travel of the wave along the medium. So this is the medium, string is the medium, okay? And we have particles on this medium, and wave moves to the right side, but the particles on the medium only moves up and down, okay? So then the wave is called as transverse wave. Do we have any question in this part? Okay, then let me discuss the longitudinal wave. Here you see a piston, okay? This one within this picture, we have a piston and we have liquid. You can consider oil, okay? Within this tube, we have liquid. And then by applying force on this piston, you can move the piston to the right, okay? So when you move the piston to the right, you will compress the liquid within this volume, okay? So you can have liquid or gas within this volume, and by applying a force by using this piston, so you will compress this liquid or gas. Then you will produce longitudinal wave, which also moves to the right. What about the motion of the particles within the fluid? So the motion of the particles of the medium are back and forth along the same direction that the wave travels. So what happens to the particles? Let me clean the upper figure and then let me continue. Just consider that here you have a particle within the liquid and here you have another particle, okay? And just consider that you are applying force to the right side and you compress the liquid, and then you apply force in opposite direction, and then you decrease the pressure within the tube, okay? Then what happens to the positions of the particles? Particles are moving like this. So let's consider we are looking for this particle on the left side. So it is moving like this, okay? So what do you see here? This is periodic motion or simple harmonic motion. And look at the motion of this particle. It moves with periodic motion, okay? So what about the direction of the wave? Wave travels to the right side with some certain v velocity, but the particles oscillate with some certain amplitude within the liquid, okay? And this oscillation, this motion of the particles parallel to the direction of the wave, okay? Look at the previous case. In the transverse wave, this is the direction of the motion of the wave, okay? But what about the particles? Particles are moving perpendicular or transverse to the direction of travel. So the particles here also have periodic motion, okay? So they oscillate around equilibrium, but their oscillation, their motion is perpendicular to the velocity. But here, in the case of longitudinal waves, this is the motion of the wave, and this is the motion of the particles, and they are in same direction, okay? The motion of the particles of the medium are back and forth along the same direction that the wave travels. For this reason, we call this a longitudinal wave. In Turkish, transverse eni ne demek arkadaşlar? Longitudinal da boyuna demek. Do you have any question here? And let me show you another type of mechanical wave. Here we have a combination of longitudinal and transverse wave. So here there is a board, okay? This one, there is a board. At the beginning, this board is here at rest, and you apply back and force, okay? Then you produce a wave on this liquid, and this wave travels to the right. But what about the particles within this wave? The particles within this wave have two types of motion. Here we have longitudinal and transverse waves. So particles have this motion, and also they have this motion, okay? So this is the combination of longitudinal and transverse waves. So now let me discuss the three important properties of mechanical waves. So the first one, in each case, we have discussed three examples: transverse waves, longitudinal waves, and also a combination of them. So in each case, the disturbance travels or propagates with a definite speed through the medium. Okay, this speed is called the speed of propagation or wave speed, and shown by this symbol for the speed. Okay, and the second one, the medium itself does not travel through the space. Look at the example here. In the first case, here you have a particle, here you have a particle, here you have a particle, and this particle moves like this, okay? So this particle does not move to the right or to the left, it moves perpendicular to the motion of the wave, okay? So here, look at this longitudinal waves. Let's consider here you have a particle, and particle has a periodic motion with some certain amplitude. It does not move to the right, okay? It has just a periodic motion with some certain amplitude. And also here you have particles, okay? And particles are moving like this, okay? And they also have this type of motion, okay? Both periodic motion and transverse motion, but they stay at the same position more or less, okay? So this explains this one. The medium itself does not travel through space. Its individual particles undergo back and forth or up and down motions around their equilibrium positions. So the last one, the last property of mechanical waves, to set any of these systems into motion, we have to put in energy by doing mechanical work on the system. So you would like to produce a transverse wave here, you have to apply force and you have to put an energy into the system, okay? Then this energy is transferred by this wave. And here you have to apply a force and you have to put an energy into the system, and this energy is transferred by wave. And here again you apply force and you put an energy into the system, and this energy is transferred, okay? So this is the last property of the mechanical waves. So here we have very important statement. Let me also discuss this one. Waves, mechanical waves, transport energy, but not matter. Material particles are not transferred. They are staying at same position around the equilibrium. They oscillate, they move back and forth, up and down, but they do not travel within the liquid or within the material, but the energy is transported, okay? Energy is transported from one region to another region within the medium. Another important thing here is that just keep this information in your mind. if you are talking about mechanical waves, it means that we are talking about the waves propagating in a medium, okay? Mechanical waves travel in a medium. They require a medium to travel, but this is not the case for electromagnetic waves, which we will discuss in physics too. Electromagnetic waves do not require a medium to travel, to propagate, but mechanical waves propagate in a medium. So this is the difference between mechanical waves and electromagnetic waves. So here, let me also explain these three properties of the mechanical waves in this example. For example, here there are spectators, okay, and they are doing the wave at a sports stadium, okay? So they produce mechanical wave. So the disturbance propagates through the crowd, but there is no transport of matter. So none of the spectators moves from one seat to another. Here, there is one guy, okay? So this guy or a lady here moves up and down, okay? The motion is up and down. So he or she stays at the same position, okay? He or she does not move to the right or does not move to the left. So he or she has this type of motion up and down, okay? So none of the spectators moves from one seat to another, but the wave is moving with some certain speed, okay? Wave moves, but particles do not move. So this is very important in mechanical waves. Do you have any question until this point? And let me continue with periodic waves. Just keep the information of periodic motion or simple harmonic motion, which you learned during the last lecture, okay? So always remember the periodic motion in this part of the lecture. So for a periodic wave, each particle of the medium undergoes periodic motion. Look at the string example. You apply a force up and down, okay, and then you produce a mechanical wave in the string. And here we have a particle, let's consider, and this particle moves up and down with periodic motion, okay? It has certain frequency, it has certain amplitude, it has certain angular frequency, okay? So we have discussed all the things in the periodic motion chapter. And the wavelength of a periodic wave is the length of one complete waveform. I will show you later on. And the speed of any periodic wave of frequency is this one. The speed of periodic wave. So this wave produced by some certain force moves to the right with some certain speed, and this speed depends on the wavelength and also frequency. Okay, so now let's discuss this information here. Here you see a mass. Look at this one, very easy to understand. If you understand this example, you can easily understand other parts of the lecture. Here we have a box, a mass, okay? And this mass is attached to a spring. Here we have a spring, okay? And then at the beginning, this mass is staying at equilibrium condition, okay? And then it does not move. And a rope or a string is connected to this mass. You see, this is a string, initial condition of the string. This string is also in equilibrium at the beginning, okay? So there is no motion, there is no movement in the system. Just consider that you move this box up and down, okay? You apply force and you destroy the equilibrium and you produce a disturbance. So what will happen? We have learned in the previous chapters that this mass will move up and down around the equilibrium with some certain amplitude. This is the positive amplitude and this is the negative amplitude, and this mass will move like this, up and down. So just remember the motion of the mass connected to a spring, okay? The same one, but vertical one. So it is moving up and down. So we have the same system here on the left side. And if this mass is moving up and down, this attached string will also move up and down. So this part of this string will move up and down, and then this will produce a wave in the string. Okay, so you produce a disturbance here in this system, which was in equilibrium at the beginning, and then you produce a disturbance and it has a periodic motion, simple harmonic motion. This mass is moving up and down, okay? And then this particle of the string attached to this mass has also this up and down motion, and this produces a wave on the string. Then we have amplitude here, same amplitude here, same amplitude here, same amplitude here, and we have motion of the wave. This wave moves to the right side with some certain speed, okay? And this wave has certain amplitude, has certain frequency, has certain angular frequency, okay? So we have discussed all these things, and all the information which we have learned in simple harmonic motion, which we have learned in periodic motion, are valid here, okay? So we have a wave here. This motion produces a sinusoidal wave that travels to the right on the string. Do you have any question here? Okay, let me show you here the wavelength. Here we have discussed the wavelength, okay? Wavelength of a periodic wave. So, and here we have a relation between wave speed and wavelength. So what is wavelength? Here I would like to show you. This is the position of this particle on the left side. Just consider here we have a particle, and just consider here we have another particle. So look at the motions of these two particles. They will have same motion, okay? So the motion of the particle on the left side will be repeated by the motion of the particle on the right side. And this is the wavelength, lambda, okay? Distance between these two particles. Let me explain in different wave here. The wavelength lambda of the wave is the distance from one crest to the next, or from one through to the next, or from any point to the corresponding point on the next repetition of the wave shape. Here we have a point on the left side, and here we have another point on the right side, and the distance in between where we have repeat the motion of the particle on the left side, we have distance, and this is given with lambda, And you can also consider lambda is this one. This is the crest. This is another crest here on the right side. Okay. And the distance between two crests also gives us the lambda. Or here we have a trough. Here we have another trough, neighboring trough. So between two troughs gives us lambda. Okay. This is the wavelength of the wave. Here we have another information. Here we have wavelength and here we have frequency, and wave speed depends on wavelength and frequency. So what about frequency? The frequency is a property of the entire periodic wave because all points on the string oscillates with same frequency. Here, just consider you have oscillator, okay? Here you have a mass and here there is a string, okay? And this mass is moving up and down, and here we have a periodic motion, okay? And then you produce a wave on the string and just concentrate on the motion of this particle. Look at this particle here on the left side. This particle oscillates with some certain frequency and amplitude, okay? So this particle has certain motion and this has certain frequency. And here we have another particle on the medium, and this particle has also certain motion, periodic motion. This also has same frequency, okay? So each particle on this medium has same frequency. And wavelength is this one. This is the wavelength, okay? From crest to the crest, this is the wavelength. Or from trough to the trough, this is the wavelength. Or from this position to this position, this is the wavelength, okay? Wavelength is defined like this, or this is the wavelength. So what was the definition? From any point to the corresponding point on the next repetition of the wave shape. So wave shape repeats itself, okay? Look at the shape of the wave. Here we have shape of the wave. This is a single wave, let's say. And here you will have another wave after certain time, okay? Or after certain distance. So this wave shape will be repeated. So now let me discuss a series of drops. Here we have drops, okay? Another drop here, another drop here. Series of drops falling into water produces a periodic wave that spreads radially outward. So you produce wave here and you produce also waves, okay, many waves. So you can consider this one. You can consider this one. At this level, the system is in equilibrium, let's consider. And here you have a mass and it is attached to the spring. And then this has certain motion, periodic motion with amplitude A, okay? And then it moves up and down, okay? And then you produce wave. So this is same. You use drops falling into water, okay? And then they produce these waves. So what about the wavelength in this case? Wavelength is this one. This is the crest, this is the crest. Or here we have trough, here we have trough. This is also the wavelength, okay? Because the wave shape is repeated. within this distance. So this is the wave in the water, and here we have the wave crests and wave troughs are concentric circles, and the wavelength lambda is the radial distance between adjacent crests or adjacent troughs. Here we have adjacent crests, and this gives us the lambda. Here we have adjacent troughs. This gives us the lambda. Okay. Here we have adjacent crests, gives us the lambda, or adjacent troughs gives us the lambda. Okay. Or the repetition of the shape between these points occurs, and then this gives us the lambda. This is the wavelength. And frequency for each particle on this medium is same. So here we have a particle, it oscillates with some certain frequency. Okay, here we have a particle, it oscillates with some certain frequency, and each particle oscillates with same frequency. Okay, they have same frequency. Don't forget this one. Do you have any question here? Now let's discuss this information in periodic longitudinal waves. Here in the picture, we have a long tube filled with a fluid. Okay, just consider oil, and we have piston here on the left side. On the left side, we have piston. This is the piston. Okay, this is the piston, and just consider that we move the piston back and forth in simple harmonic motion along a line parallel to the axis of the tube. This is the axis of the tube. Okay, and then I move this piston to the right, and then I move it back to its initial position. So piston moves back and forth, and I move this piston with some certain simple harmonic motion. Okay, so if we push the piston in, then we compress the fluid, we compress the oil, let's say, near the piston. Okay, close to the piston, you compress the oil, and this region then pushes against the neighboring region of the fluid, and so on, and a wave pulse moves along the tube. So you move the piston into the fluid, and then you compress the fluid around this piston, and then this motion is transferred to the neighboring part of the fluid. Okay, then you produce a wave pulse, moves along the tube. Here we have this simple harmonic motion. I move the piston back and forth, okay, and I produce different regions in the fluid, compressed regions or rarefactioned regions. Okay, here in the compressed regions, what we have a dense fluid, and here in rarefaction regions we have less denser fluid or a zone of low density. Okay, so here we have a zone of high density, here we have a zone of low density. Here we have a region with high density, here we have region with low density. Okay, so due to the simple harmonic motion of the piston, you produce compression and rarefaction within the liquid. Just look at the behavior. Here we have dense region, here we have low density, here we have high density region, here we have low density. Then it repeats itself. There is a repetition. Okay, then the distance between two dense regions gives us the wavelength lambda, or the distance between two low density regions gives us the lambda. Okay, this is the wavelength. Here we have another definition. Where is it? This one. Wavelength lambda is the distance between corresponding points on successive cycles. So here we will investigate the motion of the particles in periodic longitudinal waves. So this piston is moving. So this is the amplitude, let's say, and where is it? This one. So this piston has certain simple harmonic motion. Okay, it is moving back and forth, and it produces a longitudinal wave in the medium. And here we have two particles. We will investigate the motion of these two particles. The particle on the left side and the particle on the right side. So due to the simple harmonic motion of the piston, this particle will oscillate like this with some certain amplitude. And this particle on the right side will also oscillate with some certain amplitude. And by time, their position will change, okay? It is like oscillation in this system. Here we have a mass, and this is the equilibrium condition. X is equal to 0, and you push the system to this condition. X is equal to A, and this box will have a simple harmonic motion around the equilibrium, okay? So this mass will have periodic motion. So these particles will have the same periodic motion which we have discussed during the last lecture, okay? And what do you see here? This type of motion, and the amplitude is given with this one. Particles oscillate with amplitude A, okay? So we have positive A, negative A, and the particles are oscillating around the equilibrium. Do you have any question here? In order to understand the periodic waves, please always keep in your mind this system. Mass, spring, equilibrium condition, and the system is staying at certain position of X. And if you release this system will have a periodic motion, simple harmonic motion, okay, around this equilibrium. So it is same. So here we have particles, they have periodic motion, and here we have particles on the water, they have periodic motion. Just look at this particle here on the left side, okay? This particle on the water will move up and down, okay? It will move like this. If you put here a ball, this ball will move up and down, okay? Periodic motion. And here on the string, this particle, for example, here, if you have a particle on the left side, and this particle will move up and down with some certain amplitude, okay? It has periodic motion. Now let me continue with example 15.1 from the book Wavelength of a Musical Sound. Sound waves are longitudinal waves in air. The speed of sound depends on temperature. At 20 degrees Celsius, it is 344 meters per second. What is the wavelength of a sound wave in air at 20 degrees centigrade if the frequency is 262 Hertz? This is the approximate frequency of middle C on a piano. Why this temperature, air temperature, is given? Because the speed of sound depends on temperature, okay? So the speed of sound is given, and frequency is given, but the wavelength is asked. So we have this formula. Speed of a wave is given with lambda times f. Okay, if you take f from this expression, you can find v over lambda. If you take lambda from this expression, you can find v over f. Okay, so within this example, lambda is asked. So we know the speed of the sound in air at certain temperature. It is given with 344 meters per second. Frequency is given 262 hertz. You can write it in cycle per second. Okay, then you can find the wavelength of the sound waves. It is 1.31 meter. So I have asked you what is this middle C, high C in piano. The speed of V of sound waves does not depend on the frequency. Here we have speed of the sound waves, okay? In this expression, speed of sound waves. If you increase the frequency, then you will decrease the wavelength. If you decrease the frequency, you will increase the wavelength. So the speed of sound waves does not depend on frequency. Hence, lambda says that wavelength changes in inverse proportion to frequency, as I have explained here, okay? So here, as an example, high C in piano, high C, also called as soprano, is 2 octaves above middle C. High C is 2 octaves above middle C. Octave means that it is 2 times bigger, okay? Each octave corresponds to a factor of 2 in frequency. So the frequency of high C is 4 times that of middle C. So in high C, you have higher frequencies. For the middle C, we have 262 hertz. And for the high C, we have 2 octave more. Each octave means 2 times. Then here we have 4 times frequency, 4 times of the middle C frequency. Then the high C frequency is given with 1048 hertz. Hence, the wavelength of high C is 1/4 as large. So if you have high frequency, then you have low wavelength, okay? If you use this equation, if you have high frequency, then you have lower wavelength. Then in case of high C, we have lower wavelength, but we have much higher frequency. Do you have any question here? Okay, let me continue with the mathematical description of a wave. During the last lecture in periodic motion, in simple harmonic motion, we have produced some equations in order to define the periodic motion, simple harmonic motion. So we will use this previous information and we will do the same, okay? So the mechanism is very simple, very simple. Just try to stay on the line. Here we have an object, mass, and it is moving up and down, okay? And it produces a wave on this string. And just consider that this is y-axis and this is x-axis. So you produced a wave by using this system here, okay? And then this wave is moving with some speed of v to the right side, okay? It travels along the x-axis. This is the x-axis. And here you have a particle here on the string where the x is equal to 0 here. You have a particle and this particle is moving up and down along the y-axis. Is it clear? You have a particle here. The particle is moving along the y-axis up and down. and the wave is moving to the right along the x-axis. And now I would like to investigate the displacement of the particle. Here on the left side, where the x is equal to 0, I would like to investigate the displacement of the particle. Here, let's consider I have a particle where x is equal to 0. I have a particle, and this particle has certain y position. Okay, so actually y is given with these two variables, x and t, and here I investigate the particle position where it stays at x is equal to 0. And this y position of the particle will change up and down by time. Okay, then this motion is given with a cosine omega t, which we have extracted, which we have found during the last lecture. Okay, the position of this particle will change up and down by time. Okay, and this displacement of the particle is given with this expression, a cosine omega t. When the time is 0, cosine 0 is 1, then y will be equal to a, maximum amplitude. Okay, this is the a, maximum amplitude. And when the cosine omega t is equal to -1, then we will have a negative amplitude here. Okay, so this particle will have motion between positive a and negative a along the y-axis. Is this part clear? Okay, then y position of the particle where x is equal to 0 is given with this expression, a cosine omega t. And instead of omega, you can use this expression, 2 pi f. Okay, then you can write this one, a cosine omega 2 pi f t. So now we have very important information. The wave disturbance travels from x is equal to 0 to some point x to the right of the origin in an amount of time given by x over v. This is also another time, okay, where v is the wave speed. So this wave we produce here moves to the right. Okay, it moves to the right. You produce a wave and then it moves to the right. So we are investigated the y position for the particle staying at x is equal to 0. And now we are dealing with another particle. Its position is x. We have investigated the motion of the particle where x is equal to 0. And here we will investigate the motion of the particle staying at x. So the motion of point x at time t is the same as the motion of point x0 at the earlier time. So here we have particle, it is moving around equilibrium with periodic motion, and here we have another particle, it is also moving around equilibrium with periodic motion, so they have same motion, okay? But motion started here. Motion started here when the x is 0, and after certain time, the same motion happens here, okay? So then I have this definition. The motion of point x at time t is the same motion of point x is 0 at the earlier time t minus x over omega. This is where we have motion when the time is t, and this is the motion where we have when the time is t minus x over v. This is also time. Okay, so then here we have time. Look at this expression. Here we have a time. Here we have a time. Instead of this t, instead of this time, I can use this expression here in order to explain the periodic motion of particle which stays in x is equal to 0. If this part is clear, then others are easy. So here, instead of time, just use t minus x over v. And here you see cosine omega t minus cosine omega x over v. Okay, if you rearrange this part of the cosine function, you can write it like this. Cosine omega x over v minus omega t. Okay, why? Because cosine negative theta can be written cosine theta. Okay, so then you can have this form of the cosine function. So we have now dealing with the position of the x particle. Let's consider that here we have a particle where the position is x, okay? And I am dealing with the motion of this particle by time. So the particle is staying at x, and by time its y position changes, okay? This is the y-axis, its y position changes, and then I will investigate what happens to the position of the particle. At the beginning, I have explained the y position of the particle stays at x is equal to 0. Now I am investigating the y position of the particle which stays at x, okay? So then it is given with this expression, a cosine omega x over v minus t. X is the position of the particle, this one, x coordinate, and v is the wave speed. Here we have omega angular frequency, which is given with 2 pi f. Is this part clear? With this formula, I have investigated the displacement of the particle here along the y-axis, where the x is equal to 0. And with this one, I am defining the y position of the particle here, which is staying at x. Okay, so we have this definition. So here we have omega. Instead of omega, you can write 2 pi f. Here we have a wave speed. Wave speed is given with lambda times frequency, which we have discussed in the first part of this lecture. Okay, so you can rearrange this cosine function. Then you can write it like this. 2 pi x over lambda minus t over t. T is this capital T is the period. Lambda is the wavelength. Okay, so you can use both of them. They are same. So this is the wave function for a sinusoidal wave propagating in positive x direction. Let me continue. Here we have 2 pi over lambda. You see, 2 pi over lambda. Instead of 2 pi over lambda, I can use wave number. K is the wave number and can be written with 2 pi over lambda. Okay, then you can rearrange this cosine function, and you can also write this one like this. Okay, so what we have here, this wave function for a sinusoidal wave propagating in positive x direction is given with this expression. This y is the position of particle, displacement of particle as a function of time. Okay, so this particle is moving with periodic motion along the y-axis, and its position changes by time, okay, and it is given with a cosine x minus omega t. Omega is the angular frequency and k is the wave number, x is the position. So if you would like to investigate the displacement of this particle along the y-axis, then you have to change the x within the equation. So here we have x1, here we have x2, so then here you have x, here you have x. Depending on the particle on the wave, you can choose the proper x, then you can investigate behavior of this particle along the y-axis. So then we have wave function for a sinusoidal wave propagating in positive x direction, which is given with this expression. What do you see here? During the last lecture, we have defined the x with this one, a cosine omega t, right? In order to define the periodic motion of this mass, for example, around the equilibrium. So x changes by time. This object has certain frequency and it oscillates around equilibrium with some certain amplitude and some certain angular frequency. So then here we have more or less the same equation, oscillation of the particle, periodic motion of the particle along the y-axis, which is given with some certain amplitude and with this cosine function. This is the angular frequency, this is the wave number. Do you have any question here? As I told you at the beginning of this part of my lecture, the behavior is periodic motion and simple harmonic motion. If you understand the periodic motion, simple harmonic motion, you can easily understand the mechanism of mechanical waves. Now, let me continue with the wave function graphs. Here you see x-axis, here you see y-axis. So we have found this equation, okay? Then just consider that when the time is 0, what is the shape of the string? Let's consider that you have a string and you apply a force by hand, okay, in this direction, or with some certain system, you applied a force and you produced a wave on the string. And when the time is 0, what is the shape of this string? We are dealing with the shape of the string, okay? Within this equation, here instead of t, just use t is equal to 0. And here you have t, just use t is equal to 0. Then the equation will be like this, a cosine kx, because t is 0, okay? Then instead of k, you can write 2 pi over lambda, because k is given with 2 pi over lambda, okay? Then what we have here, depending on x, we have different y position, okay? So this is the maximum amplitude, and this is the shape of the string when the time is 0. And this is the wavelength. You can also measure it like this. This is also wavelength. And this is also wavelength. They will give you same result. So now let's discuss another condition. When the x position is 0, what about the position of particle as a function of time? Okay, so here x will be 0, this x will be 0. If you put 0 here, then you will have a cosine minus omega t. Since cosine negative theta is equal to cosine positive theta, then you can write it like this, a cosine omega t. Instead of omega, you can write 2 pi f, or instead of omega, you can write 2 pi period, okay? So here we have 2 pi period here instead of omega. Then we have the y position of the particle as a function of time. So this time on this string, let's say here we have a particle, and by time the position of this particle changes, okay? Then here we have this type of behavior. Don't forget, the curve here shows the displacement y of the particle, which stays at x is equal to 0 as a function of time. So here we have time, here we have y, okay? These are completely different graphs. Do you have any question here? Then let me discuss something else here in wave function. In the previous case, we have discussed that the wave is moving along the positive x direction. Okay, the wave propagates with some certain speed along the positive x direction. But what happens if the wave is propagating along the negative x direction? If the wave propagates along the negative x direction, instead of time here, we will use this expression, t plus x over v, okay, instead of time. If the wave propagates along the positive x, we have used t minus x over v. We have done it, okay? But if the wave propagates along the negative x direction, then instead of time, you will use this one. Then you will get this expression. What do you see here, which is given a cosine kx plus omega t? Here we have minus omega t. If the wave travels along the positive x, here we have minus omega t. But if the wave travels along the negative x direction, it is given with plus omega t. Okay, this is the sinusoidal wave moving in negative x direction. Let me continue with this example 15.2, wave on a clothesline. Clothesline, elbise asılan ip. Cousin Throckmorton holds one end of the clothesline taut and wiggles it up and down sinusoidally with frequency 2 Hz and amplitude 0.075 meter. Just consider that there is a clothesline and it is taut. What is the meaning of taut? Çok gergin. And then you apply force and you produce a wave on this clothesline, okay? The wave speed on the clothesline is 12 meters per second. When the time is 0, trapeze end has maximum positive displacement and it is instantaneously at rest. Assume that no wave bounces back from the far end. Question A, find the wave amplitude A, angular frequency omega, period t, wavelength lambda, and wave number k. B, write a wave function describing the wave. C, write equations for the displacement as a function of time of trapeze ends of the clothesline and a point 3 meter from that end. So omega is given with 2 pi f, frequency is given 2 Hz, 2 cycles per second, and then you can calculate omega with 12.6 radian per second. Period is S, period is given with 1 over frequency, which is 0.5 second, and lambda is given with speed over frequency. Speed is given 12 meters per second, frequency is given, then wavelength of the wave produced by the cousin Throckmorton is 6 meters, and wave number is given with 2 pi over lambda, 2 pi radian, and lambda is this one, and wave number is given with 1.05 radian per meter. And second question, write a wave function describing the wave. Wave function, look at the equations which we have calculated here. Here we have wave function, okay, which includes x, v, t, omega. Here we have wave function which includes x, lambda, and period. And here we have wave function which includes kx minus omega t. So this is the wave function. So if you know the wave number, if you know the x, if you know the omega, if you know the time, you can produce the wave function. So we will do that. We use this equation 15.4, we have already calculated. Wave function is given with a cosine 2 pi x over lambda minus t over period, okay? And then x, you don't know for certain time. So y position depends on x and t. X is here, t is here. Wavelength we have calculated 6 meter. Period we have calculated 0.5 second. What about amplitude? This is the amplitude, 0.075 meter. Amplitude is given. Just put the amplitude here. Then we have this wave function, okay? And write equations for displacement as a function of time of trache's end of clothesline. So trache's hand is here. Then I can take this one is x is equal to 0, okay? So then I can find the oscillation of particle here when the x is equal to 0. So instead of x, just use 0. Then you can calculate the wave function. And another wave function for a point 3 meter from that end, when the x is 3 meter, then you can find the wave function. Just put here 3 meter. Here we have 3 meter over 6 meter. Then you can find this wave function. Okay. Do you have any question related to this example? Let me continue with the particle velocity and acceleration in a sinusoidal wave. So again, the discussion is same with this mechanism. Just remember this periodic motion and simple harmonic motion around this equilibrium. So just consider at the beginning, this mass is staying at x equal to a, okay? And then you release this mass and it has this periodic motion around the equilibrium. And here around the equilibrium, it has maximum speed, and around this maximum amplitudes, it has maximum force and maximum acceleration. We have discussed all these things, okay? Speed and acceleration in periodic motion, in simple harmonic motion, we have discussed during the last lecture. So the same mechanism also applies here. So we have wave on a string, let's consider, okay? And this particle here on this string, and then it moves back and forth, okay? And I would like to calculate its speed and acceleration as a function of time, okay? Vy, ay. So we have calculated y position of the particle for certain x and time. It is given with a cosine kx minus omega t. If you take time derivative of this one, you can calculate y velocity. Here I have a partial derivative symbol. It is important. Here I have two variables. One is position, x position. The other one is time, okay? Position, time. And here, in case of this derivation, I only derivate this equation with time, okay? This is the partial derivation. Then, if you take the time derivative of this one, you will get omega a. This is the time derivative of the cosine function sinus kx minus omega t. So now we have velocity, okay? Transverse velocity of the particle. So velocity changes by time, like velocity of this mass attached to spring changes by time, okay? Same mechanism. So if you would like to calculate the acceleration of any particle in this sinusoidal wave, then you have to get the second partial derivative of this y, okay? So we only derivate this system as a function of time, and this is the second partial derivative of this y equation. Then you can calculate the acceleration of the particle here. Acceleration of the particle. So this particle moves up and down, okay? And its velocity changes, its acceleration changes, its y position changes by time, okay? So this equation gives us its y position as a function of time. This equation gives us its y velocity as a function of time, and this equation gives us its y acceleration as a function of time. So what do you see here? A cosine kx omega t. This is yxt, okay? And then I can write this y acceleration of the particle with this expression, okay? So up to now, I derivate this equation as a function of time. But what happens if I take x derivation of this equation? Here, just take second partial derivative of this equation, okay, with respect to x. So then we have this one. Here, we have second partial derivative of this equation with respect to time, but here we have second partial derivative with respect to x, okay? So then we have this result, minus k square a cosine kx minus omega t. So we have just done this one. Xt is given with a cosine kx minus omega t, okay? So you will get the second partial derivative of this function with respect to x. Then we have this expression. So what do you see here? Here we have calculated second partial derivative of this y equation with respect to time, and then we have this equation. Let me write this one here. D square yxt dt square is equal to minus omega square y xt, okay? And if you take this one, then you have this result. So here we have yxt, here we have yxt. Then by using these two equations, you can get this expression. This is the second partial derivative of the y with respect to time, and this is the second partial derivative of y with respect to x, and it is equal to omega square over k square. Here we have minus k square, and here we have minus omega square. Then within this equation we will have omega square over k square, okay? And remember that omega is given with this expression, v times k, okay? Then if you put here v square, k square, then finally we will have this expression, okay? So we have this wave equation, which involves second partial derivatives of wave function. So we have second partial derivative of wave function with respect to x on the left side. And here we have second partial derivative of wave function with respect to time. And we have this one. V is the wave speed. This is the wave equation, and it includes both second partial derivatives. Any question here? Then let me show you the velocity and acceleration in a sinusoidal wave here. Let's consider here I have a particle, okay? And this particle is moving around equilibrium, okay, like this. And here we have another particle. This particle is also moving around this equilibrium, okay? So for certain time, what is the velocity, Vy velocity, what is the acceleration, a y acceleration of the particle at certain x, okay? Just consider the particle on the string here. What is its Vy? What is its acceleration? Remember the mass attached to a spring. Everything is same. Here we have x is equal to 0, and this is the x is equal to a. This is x is equal to negative a, and the mass is oscillating around the equilibrium. Okay, so we have discussed ax and also vx of this mass. Okay, so it is same. Let's consider this is the equilibrium. Y is equal to 0. This is the equilibrium, and the particle is moving around this equilibrium. So here at this position, acceleration is 0 because around the equilibrium, restoring force is 0. Okay, just remember this force. Okay, if x is equal to 0, then F is 0. Remember from the last lecture, here you can consider like this one. Here we have Fy minus Ky. You can consider like this, okay? So if y is 0, then Fy is 0. So around the equilibrium here, Ay is 0 because force is 0. Here Ay is 0. Here Ay is 0. And here at the maximum amplitude, here we have maximum acceleration, but with different directions depending on the direction of the restoring force. You can consider like this. The mechanism is same. There is no new information here. So you can also understand this graph by using these equations. Look at the Ay here. Ay as a function of time and x, okay? And here we have Vy as a function of time and x. So if you use these equations, you can also understand this graph, okay? But as I told you, you can also understand this graph if you compare with the periodic motion of the mass attached to spring, which we have discussed in the periodic motion. And here we have the same wave at different times. Here we have the wave with time is equal to 0, this one, and we have the same wave when the time is 0.05 period, okay? So the time is changed, and here we have a particle, let's say. What I have told you that this particle will oscillate around this equilibrium, let's say, and by time its position will change. Here we have another particle. By time its position will change. Here we have another particle. By time its position will change, okay? So the wave moves to the right with some certain speed. So now let me discuss the speed of a wave on a string. So how to get an expression for the speed, just consider here we have a string, okay? This is the string, and it is taut, ergin. You applied a force, okay? But this is a horizontal force, okay? Then we have tension in the string. Due to this force, we have tension in the string, and this tension is equal to the F, okay? And let's consider that this string has linear mass density, mu. Linear mass density is mass per unit length, okay? Linear mass density. So you can consider like this: mass of the string is given and tension in the string is given. So what about the velocity of the wave? If you produce a wave here, just you apply force in this direction and this direction, then you produce a wave on the string. And what about the speed of this wave on this string, okay? So here we have the mechanism. At the beginning, we have horizontal force F, and then we have applied an additional vertical component Fy, okay? Then each part on this string will have certain velocity due to this force, okay? Then this moment will be transferred to the other parts of the string with this speed v, or you can tell like this: disturbance propagate at wave speed v. So then what about this v? What is this v in terms of force or tension in the string and in terms of linear mass density of the string, okay? You can write this speed of a transverse wave on a string with this expression: square root of F over mu. I will not go into detail. There are two methods to get this conclusion, okay? In section 15.4, it is done. So by using two methods, you can calculate this speed of transverse wave on a string. I will not go into detail. So what is this F? Tension in the string. Don't confuse with this component, vertical component. I'm talking about horizontal component. I'm talking about the tension in the string, okay? Here, this F, be careful. This F is equal to the tension in the string, okay? Why? Because it is coming from the calculations. If you carefully check the calculations of the speed, you will see that this F is tension in the string, and this mu is mass per unit length. This is the linear mass density. So now just discuss the application of this formula. V is equal to square root of F over mu, linear mass density. These are the transmission electrical cables, and they have a relatively large amount of mass per unit length. So they have very large mu, okay, and they have low tension on the strings, okay? So tension force is low. Then if the cables are disturbed by a bird landing on them, let's consider bird landing on this string, let's say, okay? So this will produce a disturbance on this transmission electrical cables, okay? Then you can consider it will produce a wave. But what about the wave speed? Since the tension on these cables is low, here we have low tension in the equation, and since these cables have a relatively large amount of mass per unit length, then the speed of the wave will be very low, okay? So then the transverse waves produced by this bird will travel along them at a low speed. The speed of this wave will be very low. And here, let me show you a bio application of the transverse wave. This is the eating and transverse waves. So what do you see here? This is the esophagus from mouth to stomach, okay? Swallowing food causes peristalsis, in which a transverse wave propagates down your esophagus. The wave is a radial contraction of the esophagus that pushes the bolus toward the stomach. So here there is a bolus, food, okay? And what do you see here? This is contracted, okay? Here you have some certain amplitude, let's say, and here you have different amplitude. And with this motion, this bolus moves to the stomach. Unlike the speed of waves on a uniform string, the speed of this peristaltic wave is not constant. In case of this wave on a string, this speed is constant, okay? But here, the speed is not constant. The speed averages about 3 centimeters per second in upper esophagus here. But here, it is about 5 centimeters per second. And here, it is about 2.5 centimeters per second. This is the bio application of transverse waves. Okay, this is my last example, and then with this one, I will finish my lecture. Calculating wave speed, example 15.3 from the book. One end of 2 kilogram rope is tied to a support at the top of a mine shaft, 80 meters deep. This is the support, and we have a guy here and another guy here, and this is the rope, okay? And this is the mine shaft, maden kuyusu. And the mass of the rope is 2 kilograms. The rope is stretched taut by a 20 kilogram box of rocks attached at the bottom. Here we have box of rocks, okay, and it is 20 kilogram, okay. Then this rope is taut, çok gergin. A geologist at the bottom of the shaft here. There is another guy, geologist. He signals to a colleague at the top by jerking the rope sideways. So he produces or she produces a disturbance on the string, and then this will produce a wave on the string, and this will be transferred to the friend here at the top, okay? What is the speed of transverse wave on the rope? The speed of the wave is asked. If a point on the rope is in transverse simple harmonic motion with frequency 2 Hz, how many cycles of the wave are there in the rope's length? Then what about the speed? Speed is given with this expression, which we have discussed now in the previous transparencies. So I have to find the tension on the rope, tension in the rope, and I have to find the mu, mass per unit length, okay? So tension in the rope can be found with this one due to the box of rocks. This is the mass of the box of rocks, 20 kilogram. This is the G, 9.8 meter per square second. Then F, tension in the rope, is found. What about this one? Mu is given with mass over length. mass of the rope is given, length of the rope is given, then you can calculate mu, and then just also put this one here in this equation, then you can calculate speed, 88.5 meter per second. This was the answer of first question. Second question, you can calculate lambda wavelength. Okay, wavelength is given with v over f. V is velocity, speed of the wave, which we have calculated. Just use it here. And frequency is given 2 Hertz. Where is it? It is given here, 2 Hertz. Just use 2 Hertz, 2 cycle per second. Then you can calculate wavelength is this one, 44.3. So what was the length of the rope? This one. Then you can consider that this is 40 meter, let's say. And 44.3 is somewhere here, just consider. And we have this wave here. Let's consider we have wave like this. Okay, so this type of behavior. So wave produced by this geologist, and then it moves with some certain V to this guy here. And this is the wavelength of the wave. And this is the length of the rope. This is the wavelength of the wave. Then we have 1.81 wavelength. So we have one complete wave here. This is the one complete wave. And here we have not completed wave, let's say 0.31% of one wave, let's say. So in total, we have 1.81 wavelengths. Do you have any question? With this one, I finish my lecture. Next lecture, we will continue energy and power in a wave, and we will also discuss the standing waves, and we will discuss the importance of standing waves in many applications. We will also discuss the importance of the standing waves for the musical instruments. Take care of yourself. Bye-bye.